Welcome to Invented Arizona. I'm Paul Tamarkin.
And I'm Taylor Hudson.
We're with Tech Launch Arizona, the office of the University of Arizona that commercializes inventions stemming from research. Today we're talking with Pierre Deymier, Department Head of Materials Science and Engineering at the U of A College of Engineering, and Keith Runge, the department's Director of Research. And Taylor, we're going to be transported into the weird world of quantum computing today, right?
Yeah, but I will admit quantum computing is not my area of expertise. So I'm going to let Pierre jump right in and simply tell us what quantum computing is.
So a conventional computer, that like your laptop, works as follows. What it does is it has computer chips and it has processors that are going to process numbers, zeros and ones. So these are digital processing units. And they can take a 0 and convert it into a 1, or they can take a 1 and convert it into a 0. And that's basically how these computers work. You can encode information in those zeros and 1, and you can manipulate these zeros and 1 and do operations and do all kind of things that you already do on your computer. In the world of quantum mechanics, there are quantum objects like electrons or molecules and so on. These are typically tiny objects that can be in what are called superposition of states. What they can do is they can exhibit, and we're going to talk about quantum systems that exhibit only two states. Up is expressing a 0 and down expressing a 1. So this is, up to now, it's very similar to a digital system. However, quantum mechanics allows this system to be in a superposition of states. So it can be in the 0 and the 1 state at the same time.
Okay, interesting, because I never really understood how all that worked. So now that we have a simpler understanding of the basics of quantum computing, what are some of the drawbacks to standard quantum computing methods?
When you put one of these quantum bits in a superposition of states, 0 and 1, unless you can really isolate it from the rest of the universe, it may interact with the rest of the universe and become unstable, and it's going to lose the superposition of states that it's in. So what it's going to do is going to say, I'm going to not be in my superposition of state, I'm going to be in one of the two states that I was in, and that's it. And that's called decoherence. So it's very difficult to stabilize those superposition of states. It's even more difficult when you have many qubits with each other, because then you have even less, a lot more interactions, possible interactions, and therefore you have even less stability. So you have more chances of decoherence. In quantum systems, or quantum computers, to stabilize those qubits, what people do is they need to cool those qubits at cryogenic temperatures. So cryogenic temperatures, these are very, very, very low temperatures near the absolute 0, and that requires a massive amount of energy and power and a whole cooling system around this quantum computing chip.
It seems like decoherence is a big factor here. So how does your technology address that challenge?
Our invention, or our technology, is saying we do not need quantum object to create superposition of states. And we found a system that does that, and we called it, it's based on a phononic structure that basically is supporting sound waves instead of electronic waves or other kind of quantum waves. And what happens, so we do not need a quantum system, and therefore we don't have the problem of quantum decoherence. So we can avoid that drawback by working with what we call a quantum analog, and our systems are acoustic quantum analogs of qubits, and we call them Phi-Bits. So they exhibit the same capabilities of having superposition of states, but they do not have the drawback of decoherence. They are stable.
Okay, so with your Phi-Bit, you have the ability to control and know the state of the bit, and you can run it at room temperature instead of absolute 0, and you can do all of these things while overcoming the state of the art. That's pretty cool. So Keith, while we have you on the phone, where will you see quantum computing fitting into our lives in the future? Could it, say, replace the computer we're using right now to record this podcast?
It's important to realize that the processing that quantum computers do is qualitatively different from digital computers. So we're not going to be adding and subtracting numbers with quantum computers. But recently you may have heard of advances in big data. In big data, there's this mountain of information from which you're trying to learn one or a number of things. Quantum computers are particularly good at searching. So quantum computers joined with big data leads to the possibility of very rapid examination of correlations in big data and then new insights that the data can generate much faster than a digital computer.
And I understand congratulations are in order. Earlier this year, you, Keith, and another professor, Pierre, received a very prestigious award of nearly $2 million, half of it being from the Keck Foundation and the other half being from the University of Arizona. Tell us a little bit about the work you're doing for that grant.
The Keck Foundation really funds research that cannot be funded or will not be funded by traditional federal sources, for instance. So we had to demonstrate that places like the National Science Foundation would not fund that research because it's too out there. The paradigm it's too revolutionary for them to fund. So the Keck Foundation is funding that, and as part of that, we have 3 years of work, and we have to demonstrate some of the components of this quantum computer. And at the end, we have to demonstrate a set of Phi-Bits, and I think we were stating 10 Phi-Bits coupled to each other, on which we could operate and have, in fact, operate with one algorithm, a well-known quantum algorithm, which is called the Deutsch-Josa algorithm, and so have a tabletop system operating.
Well, we look forward to hearing the results of that development towards the end of the grant. Thanks so much for taking the time to talk with us today.
Well, Taylor, thank you so much for bringing us all together. This was really fascinating. I expect we'll hear more about quantum computing as time goes on.
And thanks to all of you for listening to Invented Arizona.
For more information about this invention and all the other great inventors and inventions from the University of Arizona, visit TechLaunch Arizona on the web at techlaunch.arizona.edu.
We are at TechLaunchAZ on Twitter, and you can also find us on Facebook and LinkedIn.
And as always, we invite you to subscribe to our monthly newsletter for stories, updates, and events from around the University of Arizona innovation ecosystem.
You can find that at bit.ly/TLA subscribe.
Talk to you next time.